Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 51 of the course Theory of Computation. In lecture 50, we started the proof of Cook-Levin theorem, right? So the Cook-Levin theorem states that SAT is NP complete. So which involved showing that SAT is in NP and all the languages in NP can be reduced to SAT, right? So the first part is easy. The second part is where the challenge of the proof lies, right? And the reduction goes, so we have to take an arbitrary NP language A and we have to show that A reduces to SAT, right? So the way we went about it is using this computational table. So we showed that the idea was to construct a Boolean formula which has a satisfying assignment if and only if A is in, the given string W is in A, right? So in other words, instead of checking directly checking W is in A, we want to check whether the decider for A, the non-deterministic decider N for A, does there exist a valid computation for N on W that will lead to W getting accepted on N, right? So this is what we want the formula to check. Okay, so let me repeat. We want the Boolean formula phi to encode whether there exists a accepting computation for N on the string W, right? So N is a non-deterministic decider for the language A, right? So W is in A if and only if the non-deterministic decider can accept W, and that can happen only if there is a sequence of configurations that leads N to acceptance, and this is what we want to encode in the Boolean formula phi, right? And the details we discussed in the previous lecture. So we had to check three things or four things. One is whether the formula, whether the configurations is the valid starting configuration, and does it end with an accept, and whether the variables encode encode the table properly. So these three things, these three parts we saw in the last lecture. The part that was remaining was to check whether each configuration listed here, right, is that a valid successor of the previous configuration. So this is the part that is remaining to explain. So this part of the formula is called phi move, and this is what we have to discuss, right? So the point is that we have to check for each, like whether the first configuration is a valid, the second configuration is a valid successor of the first, the third is a valid successor of the second, and so on, right? And the main idea here is that the Turing machine computation is a very local phenomenon, and instead of actually checking whether the entire configurations, we will do a sort of a local check, right? So what we do is we will divide the entire think of there being like windows like this. So when I say window, I am talking about a part of the table which has 2 rows and 3 columns. So what we will do is think about this window moving, like so one step. So now we check this window, and the next time we check the window, similar window but moved one step to the right, and then we check another window that moved one more step to the right, and after which you check some window like this, right, and like one step below, and so on. So basically we tile the entire table using these windows. So of course there will be overlaps, and we want the overlaps to be there, right? So for all possible such 2 by 3 windows we want to check. So what do we want to check? I will explain that. So basically we define or we divide the entire. So divide is not the right word, because we cover is the right word. They cover the entire table using these 2 by 3 windows, right? And there will be overlap. So if there is a window like this, there will be, maybe I'll use another color. The next window will be something like this. So which everything moved one step forward, and the next window will be again this, and yet another window will look something like this, right? So one step below, right? So we cover the entire table using these 2x3 windows, and then we check that these 2x3 windows are valid. This is going to be the strategy. Think about the entire table covered with these 2x3 windows, and we are going to check all these windows that they are valid. So now what constitute valid windows is what we have to explain, and why covering and checking these 2x3 windows is enough, right? Right. So phi move is the formula. So we want to check each configuration whether it's a valid successor of the previous one, and the idea is that it is enough to check all the 2x3 windows, right? So what is a valid window? A window is a valid window if it is a part of a valid transition. So if there are two configurations, and so for instance, let's say, we saw here, so for instance we saw here the window that is marked over here, right, where A Q8 W2 A B Q3. So the Q8 was in the center here, and after some valid move, the tape head moved to the right. W2 was overwritten by B. So this is a valid window because it appears, and so will this be. This will also be a valid window, whatever appears here. So here maybe W3 W3, Q8 W2 W3, and below B Q3 W3. That's also a valid window, right? Anything that can appear in the as part of a valid computation is a valid window. So now let us just to get a feel for this, let us try to understand, right? So suppose as part of a computation you have BQA, meaning the way to look at it is, if you look at the Turing machine, so you have B here and you have A here, and the head is pointing at A and with state Q. So what we are doing is that, suppose this tells us to move right one step, right, and A is overwritten by some symbol, let's say D, right, and then maybe something else is read, and Q becomes R, the next state is R, right? So that is captured by this thing here. When we are reading QA, one of the possible moves is to write D onto the tape, right, and then go to state R and then move one step right. So that is what this indicates. Delta QA contains RDR. So notice that this is a non-deterministic Turing machine. So we don't say delta QA equal to. This is one of the many possible moves, or some possible moves, right? So we don't know how many, and where B could be any symbol, right? So when this happens, the first row had BQA, and the next, after one step, the B remains as it is. The D, the A becomes D, but then it moves one step to the left because the tape head moves one step to the right, and you have R. And whatever is the tape head pointing at will be here, but then that is not part of the 2x3 window. So that will get captured in the window when we look at in the next, when we move it to the next step. So this is a valid window, BQA BDR. So in fact, the thing that we saw here was similar. We have A Q8 W2 and A B Q3. So the roles of A's and B's have changed around, but you see why this is a valid window. Another thing is, let's say the same BQA, but instead of writing D, going to state R and moving right, we move left. So the only difference here is that RDL is in QA. So in that case, A gets replaced by D. Now the tape head moves one step left, so Q becomes R, and it moves one step left, and B comes here. So this is a valid window as well. Now this is the case when B is a symbol, and then the tape head can move one step to the left. What if this was a hash symbol? That is considered in the next case. So which means this hash symbol is there only in the leftmost end. So now the tape head cannot go left. So in that case, it remains in the same place. So again, the same rule, RDL is in QA, but if the adjacent left symbol is hash, it cannot move left because you are already at the leftmost end, right? So these are some of the valid computation 2x3 windows. There could be even more, right? So for instance, so all these three situations had Q in the center, right? What if Q is in the right? What if it is reading some symbol A over here, right? What if it was reading some symbol A over here, right? And then it moves right, writes D and goes to state R, right? So then in the right here it would be, so the A gets replaced by D and Q goes to R here, right? But then this is not part of the window. So the window is just the part that is highlighted in blue. This is not part of the window. So BCQ, BCD is also a valid window if you have this kind of a rule for any A, because A is not part of this window. It doesn't matter for which A, and whichever B, whichever C, and so on, right? In fact, B can also be hash here, right? And so another case when there will be a similar case when if the tape head moves left, it will be different. But again, I am not enumerating all the possible windows. I am only giving some ideas so that you get a flavor of what are the windows possible. There are many type of windows possible. Maybe another 7-8 types are there. But if I just keep going through the list of windows, it will become the lecture could just become quite monotonous, right? So what if the Q was in the top right, top left? Now if the tape, so now the tape head is reading A and it has to replace it with D and move one step right, then the one in the bottom is DRB, right? So again it's the same rule, RDR is in QA. Now another possibility is that, so here these three considered Q in the center, top center. Here Q was in the top left, top right. Here Q was in the top left. Again, I am not considering the case when Q moves left from here or the tape head moves left from here. I am only considering the case when tape head moves right. Once again, the goal is to not enumerate all the possible list of windows, but just do some so that you get an idea of what all is possible. Finally, another thing that is possible is some ABC at the top and the same ABC in the bottom. Maybe the state is somewhere far away. So these things do not change. So this is also a valid window, right? So here also we had such valid windows here, right? So let's say W2, W3, W4, it's the same thing in the bottom also, right? Any window that is over here will not change because the ones that will change is where the tape head is. So which is indicated by the state in the configuration, right? So the same thing in the top and bottom also is a valid window, right? So this is also a valid window. So these are some example of valid windows, right? The point is the valid window is a function of only the Turing machine. So given once the machine is fixed, the set of all valid windows is also fixed, right? It depends on only the Turing machine, the number of states, the number of variables, the number of tape alphabet, the transition rules, etc. It has no connection with the input. What is input, right? So the number of valid windows is a constant. Constant meaning it is independent of the input string, but it is dependent on the Turing machine, right? So that's what I've written here. The number of valid windows is dependent only on the Turing machine n and is independent of the input string. In particular, it is independent of the length of the input string, right? So now the point is that it is enough to check all these 2x3 windows, right? So we will tile or we will cover the entire table using these 2x3 windows, right? So all these cells will get covered by multiple windows because there is overlap. We want all the overlap, right? Only then can we ensure that things are checked thoroughly, right? And the point is that if we verify that all the 2x3 windows are valid, then it means that each configuration is a valid successor of the previous configuration, or in other words, each configuration is legally followed by the next configuration, right? It is enough to check, this claim says that it is enough to check all the 2x3 windows, right? So why is that? So suppose a symbol is not adjacent to the state, right? Suppose a symbol is not adjacent to the state. So maybe I'll just write down here. Suppose a symbol, let's say A here is somewhere and the state is somewhere far, right? So now the point is that there is a 2x3 window, right, which does not contain the state at all, right? If A is not adjacent to the state, which means it's either side is not the state, so we can consider the 2x3 window with A in the top center, and because it is not adjacent to the state, so the worst case is that the state could be here, right? But it could be anywhere, but it will not be adjacent to A. So now the thing is that the state could be here to the left of C or to the right of C or to the left of B. But whatever it is, now the symbol A will be unchanged in the next row, because the Q may enter here in the bottom left. It may also enter in the bottom right, or Q or the next state may enter, but it will not change A. So if you go through the list of all windows, all the valid windows, so you don't have to go through, you can just think about it for yourself. The top middle symbol, so this is a window where the top row does not have the state, right? This is a window where the top row does not have the state, and in such windows the middle symbol in the top row is unchanged, is the same in the bottom row. So this is what I want to say. So this A does not change. So if the symbol is not adjacent to the state, it is unchanged, right? This is what we want. So there is one, I'll just write it here. This is true because the middle symbol is unchanged in the windows that do not have the state, maybe in the top row. Of the window. So not, of course there is a state in the top row somewhere, but not in the window, right? So if the symbol is not adjacent to the state, then that symbol is unchanged, right? Which is true in the configuration as well, and this is reflected by the window in which that symbol is in the top middle. Second, suppose a symbol is adjacent to the state, we want to say that it will change in a proper way as per the rules of the Turing machine, right? That is the second thing, right? So if a symbol is adjacent to the state, we want to say it gets modified only according to the rules of the Turing machine. Why is that? Suppose A is adjacent to the state, right? So maybe so A here and Q here, and let's say B here. Now the thing is that there is a 2x3 window which features the state in the top middle, right? So A is adjacent to the state, then there is a window where the state is in the center, right? So maybe A, Q, C, right? And now the claim is that this window captures completely what happens because of the transition, because Q is in the top middle. Now the Q may move right or left, or Q will become, let's say it moves left, then C becomes D or something, and A comes here. So now the movement is only according to so this particular 2x3 window in which the state is in the top center completely captures what happens to this part of the tape, right? This, or the changes are entirely confined to this 2x3 window. This 2x3 window. So if a symbol is adjacent to the state, that symbol will feature in the window where the state is in the top middle, and that window captures completely what happens, what changes happen, right? So that window will capture everything, and so that is also fine. So if the symbol is not adjacent to the state, then it is unchanged, and if a symbol is adjacent to the state, it features in this kind of window where the state is in the top mid, and that captures all the changes. Hence, whatever changes happen are only near the state, and that is captured. And whatever is not near the state, it is unchanged because of the first part. So that completes the proof of the claim. So anything that is away from the state is left untouched, and anything that is near the state is captured by the window in which the move is captured correctly. Hence, this ensures that any configuration is a valid successor of the previous configuration, right? And also and also there is overlap, there is sufficient overlap which ensures things are reflected properly. So this is why we need to tile the thing with overlap, because we want every symbol that is adjacent to state, we want it to look at the windows where the state is in the top middle, right? So now that this is done, so now we have shown that the number of, we have told what are the possible windows, right? Or we have given some examples. This is not an exhaustive list, right? But the list of valid windows is a finite number which only depends on the Turing machine and not on the input. And second, it is enough, this claim says that it is enough to check all the 2x3 windows, right? So now we can write down the 5 move. So what is 5 move? We go through all possible windows, right? Ij is the, so the ijth window, what I mean is, by the ijth window, what I mean is this. So this is I and this is j. So this will be ij plus 1. This will be I minus 1j. This will be, sorry, I plus 1j, I plus 1j plus 1 and so on. So here will be ij minus 1. So maybe I'll just make it a bit bigger. So this is ij, this is I plus 1j, ij plus 1, I plus 1j plus 1, I plus 1, j minus 1 and ij minus 1. So when I say ijth window, I mean the window where ij is in the top middle, right? So we want to check all the ijth, all the windows, they are legal. So what I mean is, so we look at all the windows and check whether this window is a legal window by exhaustively going through the list of valid windows. So this part, the part that is, so we'll check whether it is legal. How do we check it is legal? So we know the variables here, right? What we do is, for each term like this is expanded like here. So where we take an OR of all the valid windows and we check whether this window corresponds to that valid window. So if A1, A2, A3, A4, A5, A6 is a valid window, we are checking whether the ij minus 1th entry is A1, ijth entry is A2, ij plus 1th entry is A3 and so on till I plus 1 j plus 1th entry is A6. So it's an AND over all the windows and OR over all the valid windows, and inside there is an AND, whether this window is this valid window. So whether the selected window ij corresponds to the specific valid window A1, A2, A3, A4, A5, A6. So like that we check through all the valid windows. So maybe it is not this valid window, but maybe it's some other valid window. So maybe there are 1000 valid windows. So we need to have this OR that runs over all the 1000 valid windows, right? Maybe there are 10,000, maybe there is 1 million valid windows, but it's a constant that is independent of the length of the input. It will not change if the input is longer or smaller, right? So this is 5 move. You go through all the windows ij and check whether, so when I say windows ij, I mean the entries ij in the table, and check whether this entry is equal to a valid window by just going through all the list of valid windows and checking, is this valid, is this, so basically we are doing this, right? And maybe I'll just, small pictorial explanation might help. So we have the 2x3 window that is moving across the table, and once we fix a 2x3 window, we check whether, so there is a list of valid windows given, right? So valid window 1 to 1000. So is this the first valid window? No. Is the second valid window? No. Is the third valid window, and so on. And at some point, it is, if it is a valid window, that part will say yes, and that will make this clause yes, right? So that's what we are doing here. So we are going through list of all valid windows and checking whether this particular window chosen does this equal any specific valid window, right? So that completes the reduction, right? So that completes the construction. So first let us see the correctness. So correctness has been established by what we said in the previous lecture and this lecture, that if we are checking whether this formula is satisfiable if and only if we can set these variables in a certain way, and we can set these variables in a certain way only when there is a sequence of computations that lead n to accepting w. So this formula is satisfiable if and only if n accepts w, if and only if that happens, if and only if w is in A, because n is a decider for A, even though a non-deterministic decider. Now, so this is the correctness. What remains is to show the running time of the construction. So the running time of the construction is also not that difficult, because if you see all the formula, even though it was for instance this is like n power k times n power k, etc., and here we are running a loop on delta, here again double loop on delta. However, the fact that I can write the formula in a concise manner like this indicates that I can write a loop or multiple loops, nested loops or something, for creating this formula, right? So for instance, phi cell, I can have two loops outside where I and j run from 1 to n power k, and one loop that runs through all symbols in delta here, and then one double loop that runs through like L runs through all symbols of delta and L prime runs through all symbols of delta, and output this formula, right? Similarly, phi start is basically I have x1, let's say j, and a specific symbol. So this formula also can be encoded in a loop. It's a very easily, very clear structured kind of formula, so which can easily be written down in a program. And phi accept, you just have x I j q accept, where I and j vary all vary from 1 to n power k, right? So this is also straightforward. Phi move is also straightforward, right? So we have an outside and we have an outside and that runs through all I and j, and within that there is an OR that runs through all the valid windows, and then inside that there is a 6, it's an AND of 6 literals, right? So if you look at the length of each of these formula, the number of variables which I think mentioned in the previous lecture also, there is x I j l, where I ranges from 1 to n power k, j ranges from 1 to n power k, and L ranges from has size delta, right? So the number of variables is n power k times delta, but delta is independent of the length of w, so it gets absorbed in the O, so it's O n power 2k, right? So because delta gets absorbed in the O notation. Now phi cell, if you see, this is n power 2k, but inside it is just dependent on the delta. So here there is delta, here there is delta square, so it is still O n power 2k, because this part is constant once I and j are fixed. Phi start, basically there is only one row, so it has only n power k, not even O, it is just n power k variables. And phi accept has actually n power 2k variables, again not even asymptotic, exactly n power 2k variables. So that's what I have written here. Phi cell has O n power 2k length, phi start has n power k length, phi accept has n power 2k length, okay, so there is not even O here. Phi move, for instance, has O n power 2k length because of this, so this has n power 2k, and checking whether the ijth window is legal is this runs through the list of all valid windows, and this is constant. So number of valid windows is constant, number of valid windows is also a constant that is independent of the length, right? So number of valid windows into n power 2k into 6, but this is also n power 2k. So the size of the formula is polynomial in n, everything is n power 2k, n power k, n power 2k, etc. And as we noted, they are all very concise descriptions, which means there is a way to we can easily write with some for loops an algorithm to generate this formula, because it has a very repetitive structure, right? So that completes the proof that SAT is NP complete. So the reduction part, so we took an arbitrary language A that is in NP, so we assumed that there is a non-deterministic Turing machine n that decides A. So non-deterministic Turing machine that runs in n power k time, that decides A. And we encoded the formula that we created in such a way that the formula accepts, or formula has a satisfying formula has a satisfying assignment if and only if there is a sequence of computations that lead n to accept a string w. So n accepts w if and only if the formula has a satisfying instance, and that gives the reduction. And the running time is also polynomial, right? So that completes the proof of the Cook-Levin theorem. And one key thing in the proof is that we noticed, instead of checking whether each configuration is a valid successor of the previous one, we saw that it was enough to check the validity of all the 2x3 windows. We can basically cover the entire table with the 2x3 windows and check the validity of them. And that helped bring down the size of the formula, right? So that completes the proof of Cook-Levin theorem. It's a very interesting theorem, but we need to start somewhere, right? So now that we have the Cook-Levin theorem, now it should be easy to prove some other languages are NP complete. For instance, if we want to show that a language click is NP complete, we just need to show a reduction from SAT to click, and we need to show that click is in NP. If we want to show that subset sum is NP complete, we need to show a reduction from SAT to subset sum and show that subset sum is in NP, right? So we don't need to do everything from scratch where we take an arbitrary language in NP like we took here. So I'll conclude this lecture with a couple more things, right? First thing is that 3SAT is NP complete. Okay, so what is 3SAT? 3SAT is a set of all Boolean formulas that are in 3CNF form and are satisfiable. So 3CNF means things like this, something like x1, it's an AND of OR, so x1 or x2 or x3 complement and x3 or x4 complement or x5 and I don't know, x1 or x6 or x6 complement x7, something like this. This is, so it's an AND of ORs where every AND of clauses where every clause contains exactly 3 literals and every clause is an OR of exactly 3 literals. So this is NP complete. One way is to reduce, so we have already shown that SAT is NP complete. So to show that 3SAT is NP complete, one way is to reduce SAT to 3SAT in polynomial time, right? So in all of this I am assuming that showing 3SAT as an NP is straightforward. In fact, we have already discussed it in one of the previous lectures. So one way to show is that to reduce SAT to 3SAT, right? But one way to show is to do this. Another way, instead of making a fresh reduction, what we can do is, so whatever proof we did for the Cook-Levin theorem, right? We can kind of tweak the proof so that so we got a formula phi at the end of the proof. Now, if this formula phi is a 3SAT formula with an equivalent 3SAT formula, meaning this formula phi satisfies the condition that whenever n accepts w, this phi is satisfiable, and whenever n does not accept w, this phi is not satisfiable, and this formula is 3SAT or 3CNF SAT, then this reduction itself will do, right? So it turns out that we can convert the formula that is output from the Cook-Levin proof into a 3CNF SAT instance, right? So I'll just list down the way to do it as 2 exercises. I will not write down and go into detail. So first, so we have it, the formula is an AND of 4 things, right? Phi start, phi move, phi accept, and phi sell. So a CNF means AND of ORs, AND of clauses. So we will show that each one of them is a CNF, and this is not that difficult. So phi sell is basically already an AND of something here, and so again this can be considered as one clause and this can be considered as another clause. So phi sell is already in the form of AND of ORs, so it's okay. Phi start, it's already in the form of AND of individual variables. So we can think of these as AND of singleton clauses with singleton literals. phi accept is basically an OR of many things. So we can think of this phi accept as a single clause. There is no AND. Now phi move, it's an AND of OR of ANDs. So there is AND of OR of ANDs here. What we can do is, anything that, OR and AND kind of we can distribute over each other. So this OR of ANDs, we can write it as an AND of ORs. Therefore getting AND of ORs, which again will become a CNF instance. So here we need to use the distributive property of OR over ANDs. So for instance, maybe just to give a small example, so we want to show that OR over ANDs, OR of ANDs can be written as AND of ORs, right? So OR of AND, so suppose A and B or C and D, this is equivalent to, we can write it as A or C and A or D and B or C and B or D. So you can verify that the formula in the left, so maybe I'll use a different color. The formula in the left, this is true if and only if the formula in the right is true. Right? So this is the left formula is true if either A and B are either A and B is true or C and D is true, and here also the same thing is required. So this can be verified. So maybe I'll just so distributing OR over ANDs, right? So this way we can convert each of the phi cell, phi start, phi accept and phi move to a CNF instance. And the second thing is that so that is the first exercise. The second thing is that once we get something in CNF form, we can convert them to 3 CNF form. So that is the way. So the formula generated, we first ensure that it's in CNF, then we ensure that it is in 3 CNF. So any CNF formula can be converted to 3 CNF. It's not that difficult. So suppose we have a clause. So basically we modify the clauses to ensure that it has exactly 3 literals. So suppose we have a clause x1, x2, x3, x4. We can convert it into the AND of 2 clauses where we introduce a new variable y. And now you can verify that y has to be either true or false. So if y is true, then x3 or x4 has to be true. If y is false, then x1, x or x2 has to be true. So basically by 2 choices of y, we are covering the entire possibilities of the OR. And similarly, when we have a clause of 5 literals, we can do the similar thing by introducing 2 new variables y1 and y2, which connect all these 5 original variables. And if there is a clause that contains only 1 variable or something, so if you have something like this, let's say x1, you can map it to x1 or x1 or x1. That's also, and if there is 2 also, you can repeat one of them. So that is another exercise. And finally, one more thing that I want to mention is that 2 sat is NP, right? So we said that 3 sat is NP complete, which means it's unlikely that 3 sat has a polynomial time algorithm. However, 2 sat, so what is 2 sat? It's a CNF formula, which is an AND of clauses where each clause, so 2 sat CNF formula C1 and C2 and C3 and so on, where each clause is of the form something, let's say xi or xj or something, xj complement or something like this. It's an OR of two literals, right? So two literals. So this is surprisingly this is in polynomial time. So this is something interesting because 2 sat is in polynomial time while 3 sat is NP complete, which we expect to be not polynomial time. So what happens when we go from 2 to 3, or what happens when we go from 3 to 2? So the reason is we can view 2 sat as something like implications. So this, let's say something we have xi, maybe just for the sake of simplicity I'll just take xi or xj. So it's like if xi is false, then xj has to be true, otherwise this will not be satisfied, right? So this can be viewed as implications, and that characterization helps us show that 2 sat is NP. So I'll not get into the proof here, but the key idea is that every clause can be viewed as an implication. Maybe I'll write that idea down. Key idea: every 2 sat clause can be viewed as an implication. So that's how we will show that 2 sat is NP. And that's all. That's pretty much all that I had in lecture number 51, where we completed the proof of Cook-Levin theorem, right? So Cook-Levin theorem, we want to show that sat is NP complete. We showed by taking an arbitrary NP language A. We considered the non-deterministic polynomial time decider for A, and constructed a formula, Boolean formula, such that the non-deterministic decider has an accepting computation for a given string if and only if the constructed Boolean formula was satisfiable, right? And that involved multiple steps and multiple parts and multiple reasonings. And that completes lecture 51. This is also the end of week 10 lectures. In week 10 lecture, we first saw the verifier characterization of NP. Then we saw verifier characterization of NP. Then we saw that NP has is the same as polynomial time verifiers. Then we saw reductions. We saw polynomial time reductions. We saw NP completeness, and then we saw the proof that SAT is NP complete, right? So SAT is NP complete, and using this, now we can other languages to show that it is NP complete. We do not need to show that an arbitrary NP language reduces to it. Instead, we can take SAT and reduce to the other language, right? So in week 11, we will see other NP complete languages where we will not be showing it from scratch, but from some already known NP complete languages, maybe like SAT or something that we have already proven at that time, right? So that completes week 10, and see you in week 11. Thank you.